ambitious than being bored at the end. So I want to show you how to run this in Fiji, how to install it, how to have just one example image, small one, how to do this anisotropy, how to run the actual thing and visualize the result. You know, I can tune these things. Then show you how to do the same thing for the command line. So this tool is either Fiji interactive, but you can also run it from command line. And then go a little bit into how you would do larger volumes. First, just doing a little crop of a larger volume, how you do that, and then eventually also how you run it with Spark, distributed. Just, you know, people interested. And I hope we're going to get there. And there's also mask filtering and so on. Marvin actually wrote this, so I'm not sure we're going to get to that, but you know, that's details. At the end, the important thing is all of this is as usual on GitHub. I think it was here. There's the RSFish Spark and RSFish. All this is linked from the paper and easy to find. So there to repose. The second one open. I closed it. Which has like introduction and tutorial and all these types of things. Not everything is always 100% up to date. Sometimes things change, and you might have to do a little bit, but it tries to go through all of the things that I'm showing. People made Docker containers and all these types of things. So I think it should be hopefully pretty straightforward to use. Okay, just a little background in the beginning. I mean, for those who are not like fish experts. So that's basically the idea, right? You put a single molecule fish that stains individual RNA molecules in the sample. You could also do DNA fish, there's a lot of different types of samples, but some diffraction limited spot that you want to find. Right? So I think molecule fish was the initial intention, but then we worked on the different types of samples. We started originally with Tim in Rob Singer's lab. Very nice guy, some of you know him. And just 10 years later, we already published this. Interesting. Anyhow, so so this is how these classical single fish stacks look like. You have multiple colors, often for different genes, and each of these responses one single RNA molecule. Here, magenta, cyan, or red. Right? Is this clear so far? I mean, I guess all of you know that anyways, right? So it's usually some kind of Stellaris technique that we used here, where you find about 20 to 30 of these single RNA molecules each in the tag, and then only that's why you see an RNA molecule, one single molecule you can see. But since you have 30 or 40 of an RNA, you can actually see it. So why did we do these RS?
These days you can buy the molecules already tagged with everything.
But not only these days, since 20 years. It's always been an expensive hobby though. Like one of these probe sets is like, I don't know, it's now must be $700, $800, $900 for one gene, right? So it's not that cheap. So why did we make RSFish? I mean, we weren't so happy with the existing tools since we were actually working in volumes. So many of the existing tools are good. They're not bad at all, but they're not really good for large volumes. So that was the original intention. Plus, it's sometimes not so easy to parallelize. So we had lots and lots and lots of data. There's an easy fish. The project realized this, that with the existing tools, it can be hard. We suddenly want to make a terabyte of data and process that. So either for a lot of images or for large volumes. For large volumes, it's even harder than for just like thousands of images or so on. And we wanted something that integrated the Fiji ecosystem. There was just nothing. It was all like MATLAB mostly, which is hard to use. You know, you have to buy licenses and so on. And what we also wanted is the interactive parameter selection. That you can go in there, especially for the biologist who doesn't really know so much. You can just put some sliders back and forth until it finds you more RNA molecules. Microscopy, command line tool, and Marvin at the end also made the cloud deployable software package of this. I'm not sure people actually use this because it's not so common, but you can. So from the computational side, that was the original idea from Tim and myself. There was this radial symmetry paper, which is kind of cool because it basically shows that when you intersect the image gradients in from off a spot, you get a localization that is as good as a Gaussian fit. People typically do Gaussian fits to localize these things, but it's incredibly slow because it's an iterative procedure. It just takes a lot of time. This, as you can see, is very fast, right? You simply complete the intersection point of the gradients, which is it was published in 2012. We started smoking. It could be maybe cool, could be a cool technique. And on top of this, we could basically combine this with robust outlier removal. As if two things are very close to each other, you can find which pixels belong to one spot and to the other. We'll talk about it later. Yeah, that's basically how it's all started. What we basically did is we derived this whole, so they did a two-dimensional derivation, we did an n-dimensional derivation, and the other problem that we solved is that usually things are not round. So in order to compute an intersection point, the arrows have to intersect, right? Which in XY is the case, but in Z usually it's stretched or combined, like or condensed, right? It doesn't look isotropic. Then we basically derived the formula that we in place can basically adjust the gradients, even though the images are anisotropic. What people have done before, if they use this, they simply scale the image. You can do this too, right? You can scale the image and make it isotropic, but then actually needs interpolation and all these kind of things. You modify the gradient. It's easier if you can just derive the whole thing on the images. That's basically what we did here. And as I said, we combined it with robust outlier removal, where basically the idea is that you define a certain confidence, that is green circle, which gives you the radius of saying, please only take gradients that intersect the point and are not further away than half a pixel. This is actually the old picture that is wrong, so this one should be green because it actually goes to the circle. We never changed that. But yeah, so this one should be green, right? This test, these other two should be white. So that's basically the cool thing is that if you sometimes have some points that are close to each other, you can actually separate them. I mean, to be honest, this is I need to write parameters, but this is hard. It's not something that people actually do. And there are better methods if you have a really crowded space. You would use these days machine learning based methods, and I will show one just quickly. How I would actually do this, what the problem, but it's a little bit better, for crowded spaces. And the cool thing is you have this interactive thing where you basically open your image, then you kind of simply adjust the parameters until it finds your spots. Because every image looks different, and the same idea basically applies if you want to run this at very large volumes. You take a little crop, see that it fits, and then you can basically distribute it and run it. And at the end, we also have powerful tools to visualize the result. They can actually overlay the point clouds onto large images, small images, which will also give you a feeling for if this does actually work or not. To change some parameters. The nice thing is it's pretty accurate. Honestly, they're all in the same range. There's like a little bit up and down. Also, I wrote this in the paper. A little bit better, but I think in the first revision we didn't even have this plot. People were pushing us. This is better. This is not better. And it turned out to be a tiny bit better. But I think all of this is pretty comparable. I don't think it really matters. What matters more is kind of what type of data you want to process, how big it is. Do you want to work in a Fiji environment? Do you want to work in Python? Do you want to work in MATLAB? But it's still kind of interesting, I think, to see these comparisons because all of them have their strengths and weaknesses. For example, RS fish but air localize better. Big fish and starfish don't localize so well. That can also change, right? This was the state a year ago. Then there's the processing speed, which can be important for large volumes and so on and so on. We even did basically the comparison of F1 score and localization error as a function of noise, right? So don't really see the images, no noise, and incredibly noisy at the end. Because you see which method behaves how when increase the noise level. Which I find pretty useful because usually you can just go there and see, okay, that's how my image look like. What is important to me? Do I need to localize well? Does this matter to me? Often, yeah. In the softwares can be chosen for practicality. I don't want to say that ours is better or anything. It's really just, I think they're all pretty good. There's certain ones that are not that good on certain things like Deep Link. Because Deep Link is the only published machine learning based one that's only written for 2D. So running this in 3D, yeah, it's a bit of a hack. It's just unfair. We also wrote this, but I think apart from that, all the ones are good games. So the cool thing about ours is that, for example, that we can easily run this on different kinds of samples. Easy, you can open your image in Fiji, just run this, get the CSV out, visualize this. If you have a large volume, you can nicely run this in blocks. This was actually done with the EasyFish project. But we actually did this for the first time on large volumes. Then you also have the visualization. I will show you that later, where you can basically just take these large volumes, this 150 gigabyte stack, where they can zoom in and actually see the overlay of the spots. So the red obviously detected spots, right? Then you can basically see did this work, did this not work. which is a very useful feedback because before you couldn't even look at the result. We've done the same thing actually with Tim's method with FishQuant. You can just visualize those spots as well. So I think it's also just a set of tools that you can basically use interchangeably.
Do you know if Palm Storm microscopy has already started implementing radial symmetry or non-Gaussian based fitting approaches?
I mean, for these things, machine learning based seems to be the best. It will outperform all of this.
But is that what's being employed right now for
No,
commercial systems?
We got these questions too, but I don't think it's a good choice. I mean, you can play around a bit and find some spots, yes. But I think it's a much more controlled environment with things. So these machine learning based methods, you can train them much easier and they're going to generalize much better. So Srini developed, and I just want to show that Srini is currently extending this to single fish based detection. But for Storm and Palm, I would use the machine learning based.
Oh, like this the DB techniques. I think I know of.
I will show in a second. So yeah, but I mean, yes, you can use it. It's going to give you something, but it's definitely not. I wouldn't say use it for that. I mean, you can. But, yeah. Here, this has to do with background and all these types of things. You know, it's a bit of a different problem usually that you have with single multi-fish and with just super resolution microscopy. So here, this is for our in-house system that we have the Nerfish. So we can also just visualize the results. So they have the software that they run, but sometimes it's just nice to be able to see things. Or the nice thing is in this way, you can also incorporate this easier into image analysis workflows that may exist. Right? Because we easily represent this as images. We can easily overlay this. You can use this for registration and what have you. Right? So, yeah. And specifically, the ability to overlay this with very large volumes can be beneficial for certain, especially here, I think. So the other method that Srini has been developing is decode. It was called for super resolution microscopy. They basically outperformed everything that existed. They have an open benchmarking website, and they basically use the machine learning autoencoder, pretty smart design to localize these spots as good as possible. For those who are interested, this is basically, for those who know what an autoencoder is, right? Usually you have a latent space where you train to compress your image into a representation, a small one, from that recreate the image. What it basically did is that the decoder is a physical simulation, which in this case is easy because it's simply applying the transfer function to the locations of the points, and that's the decoder. And then the encoder they actually trained. And so what the encoder gives you is actually location of all points that allow you to recreate that image. And that's a very powerful approach. And here on the right, that's the work we started doing with Habib, but he was still here. It's basically the same, the EasyFish data set, applying that to single multi-fish data, which is a more complex problem because PSF changes, background changes, brightness changes significantly, you have accumulation of, it's a much more complicated problem. But I think to your question, this would definitely outperform RSFish for super resolution. And I would use that rather than. So, little summary, yeah, scalable single fish with RSFish, the two GitHub links, RSFish and RSFish Spark. And we focus on large, but also on small data sets, obviously, and I want to show command line and Fiji implementation using command line and Fiji, and of course, that also it's all written in ImageLib on the backend, basically for the visualization processing. That's why also scales large data sets. Okay, so that was hopefully not too long. Yeah, 18 minutes, hopefully good enough. So, questions? Questions? Yeah, cool. Okay. How do you install it? So I'm going to leave this in the background just to also not forget what I actually want to do. So let's say you have a typical image, something like, I tried it out, it actually works. Like this. This is Laura Breimann in my former lab did this. So we did a lot of single multi-fish screens. So this is a C. elegans embryo expressing which gene it is. Maybe also not relevant at this point. But basically, it's nice to see all these little dots that we want to segment. So as I said before, one key feature that we need to know is the anisotropy of the data set. Right? So this basically is a combination of the point spread function extension and the sampling in Z. Right? Usually, if you would sample isotropically, it would be gigantic typically in Z, but that's why people sample in Z less, because you oversample completely if you don't need it. So often it ends up being somewhat isotropic simply because you kind of match the sampling to the extent of the PSF. But if you just look from the side, such data set, right, you see that they are a bit extended, right? They're not really round. I would argue that they're a bit bigger in this dimension than in the other, right? Here they're nicely round. Here they're not. So if you think back about how the radial symmetry works, we did round, right? We need to know the scaling factor difference. And it's not just a calibration. As I said, it's a mix of PSF extension and sampling. So RSFish allows you to extract this automatically. Just one thing I want to say, it's not super dependent on it. Because if you see that, right, even if you do not scale it, if you just compute the intersection point, it will still be here in the middle. Right? The RANSAC won't work so well and stuff. It's not like super sensitive to this. It's not, you can usually run it also with a scaling of 1. Often because usually it is close to a scaling of 1. It's not so 0.1 or 10 or something like this. Usually it's something like 0.8 or 1.2. But usually once you have this and you don't change your microscope, it's going to stay like that. Typically, if you do some sort of analysis, things stay constant. So in order to, I want to show you how to install this. I have it installed already. If you want to install it, you go to Help, Update, in Fiji. Then you select Update Site. It's called Radial Symmetry. It should be called RS version. It's called Radial Symmetry. It's all written on the GitHub too, so you can just you activate this, restart Fiji, and it's there. So that's there. Here, RSFish. And the first thing we do, you could run it as I said with a scaling of 1. That's what it will assume. But you can have these tools to compute the anisotropy coefficient for your image. And we have 2 methods. We do a Gauss fit to the spots and actually find the anisotropy. You can use radial symmetry also to find out this. So at some point we wanted to automate all of this, but it's a bit of overhead, so we made it into a separate step that you can or cannot do. Usually I do Gauss fit because it fits it once for a few hundred points. So you basically have to help the algorithm in the sense that say, okay, what are points that I can fit to? So you can just change the sigma and say, look, find me those little things. Special basically changes how many you find. And it will not show all of the points. It will show the points once you go through Z, right? So it will actually show the points in the Z layer that it would be detected, right? Now we think, oh, it didn't find this point, right? But it will find it with points in a different Z plane. Not find this one. But you know, it basically really shows just the currency plane. So if you go through, and in this case, you don't want to find all of them. That doesn't matter. As long as you find some of them, it's enough to do this Gaussian fit. Found 153 points. And it also used to use only this ROI that you selected. It will not use the entire stack. If you have a big image, you can just select a small area. It will really use only points in that area. And it gives you some anisotropy factor. A minute, yeah, 0.73. You can easily figure this out by yourself. It's basically a factor you have to apply. So it is isotropic for the sake of it. You can do that. Yeah. Which is nice. So now we scale this by 0.73 in Y, right? Because we turned it around. So should look round. That's basically the theory of it. And voila, roundish dots. Right, that's the and of course you don't have to, the point is that you don't have to do that. It will just automatically. So now we run it on the data set. There's a few questions. Most of them are clicking OK. Just to explain what it is, which image, okay, only one open. There's an interactive mode that I usually use first to find the parameters. If you want to macro record all of this, then you have to use the advanced mode. But the advanced mode, if you run it a second time, will remember all the interactive parameters from the first round. You set now interactively, if you run it again in advanced, it will pre-fill everything that you selected it actively before. That's how you would macro record it, and then basically run it for 100 images in a folder or so. It will automatically populate this anisotropy coefficient for you if you ran this before. If you restart Fidget, you have to type it in or remember. Robust fitting, as I said, we do this RANSAC where we find the gradients that only match. We can also just not do that and say just for each point that we find with the difference of Gaussian, just computer center, that's it. Or you can do the multi-consensus RANSAC. That's one that even tries to find spots that are close to each other and tries to, if for one spot says this could be 2, I try to separate, or 3, I try to separate this out. But as I said, finding the right parameters is a bit of a challenge there. So that's the default. You can provide the minute max of the image, or it will figure it out by itself. That is important when you, for example, run it for many, many images and you have bright spots in there and stuff like that. You might want to hard code this and say, in my image is always from 0 to 1000. And that's what I set the parameters for, because the parameters you set are relative to the minute max. If you load it from the image, this is what you want. If it, for example, gets darker over time or brighter over time, and you want to increase, but usually that's not the case. And what you want to do is basically provide the minute max by hand. Then, if you run it over 1000 images and say it's always between 0 and 1000, and then it will apply that. Also, when you run it distributed on a cluster with Spark, it's the same thing, because you cannot go over the whole image at a point. The image is so big that you can't first iterate all pixels to find out what's the minute max. In that case, it also asks you to provide this when you run. I don't know if you get there, but if you the Spark version will ask you, okay, what's the minute max of the image? Because otherwise it can only get it from a little block that it's currently processing, and that might be dark. And so that's why this minute max is kind of important. As I said, initially we find the difference of Gaussian, we find the spot that we then localize with the radial symmetry, and it uses this anisotropy coefficient also for the difference of Gaussian, knowing it's more or less blurred in the direction, it's just detail. You can then, so we find the location very accurate. The question is what to do with intensity. You can just do linear interpolation at that location that you find, and it will get you that. Or you can do a Gaussian fit, basically, for the intensity, right, to find the intensity values. Or you can just integrate the spot intensities on all pixels. EasyFish asked for that because they wanted it, so I did that. I'm sure if it's useful if you start fresh. It might be useful if you've always done it like that and don't want to change. And by default, it will make a list of points that you can save, or you can add the detections to the ROI manager for those who use it. Okay. So now it opens a new image, which is the RANSAC preview. I will just zoom in a bit, right? So if you have two parameters, the red is the sigma, or the initial difference of Gaussian, and the blue cross in there means yes, it's localized by RANSAC or no. Right, and you can go through Z, basically see all the points that it finds. On the right side here, you see which pixels were actually used for each spot to find the RANSAC. Here, the yellow region is just a preview, because if it's a very big window, it might be too slow to see an interactive one. It will run it on the entire image. So here, these parameters are for the difference of Gaussian, right? Like basically how big the spots are on average and how bright they are. If you go, find nothing, you find too many, so you want to find something that's reasonable. Usually, the default settings are kind of bright. Usually. And the other are the RANSAC parameters. Is basically how many, what's the radius where I extract those gradients and intersect them. So by default, it does a radius of 3. What's the inlier ratio is basically for each of the spot, how many of these pixels need to intersect, so I consider the found spot. By default, if you do 10%, it's really low. If you increase this, it will not find any ones anymore. So usually, from experience, it's okay. It will, if it's really some noise, it will anyways not find it. But you only find 10% intersect. And of course, this is all relative to the maximum error that you allow. So you say all these gradients have to intersect within 1.5 pixels. Very generous. It's very robust. If you say, look, they have to intersect very precisely, it will not find any. So yeah, that's basically, we have some methods for local background subtraction that you can also run. I've actually never used this. but you might need it on certain images that have very specific characteristics. Tim has always done this in this code. Basically, locally fit a plane to the intensities and subtract that. It's more, if you do a Gaussian fit, you're more sensitive to this than with the radial symmetry. So that's why it doesn't matter so much. Then you press done. It will run this on the entire image. It found 2,100 spots with the DVG. And of that, 4 didn't fulfill the RANSAC criteria, so not so many. Then you have a final say in basically potentially rejecting them by absolute intensity. For example, if you know, in this case, everything under 15,000 is not good, it actually actively updates this. So if you press here, the points are updated. You kind of see what's left.
So what would you do to the original image to ensure, success? Like, do you need a sufficient SNR or flat field, correction to get better results or more accurate
Sometimes
results?
we do this, yeah. So we basically compute a big median or Gaussian filter subtracted that can help.
Deconvolution beforehand.
Usually can introduce artifacts. Depends on if you slightly deconvolve a little bit for a few iterations can help. Yes, because you highlight these spots more, but you have to be careful with, can get very Poisson-y, right? The signal after.
Well, I'm just wondering because right now, if you're doing two things right now, you're detecting spots, but you're also using the same image for intensity calculation. So some might just want the localizations and then use maybe a more really raw, unprocessed image to get the original signal.
But you could do this, right? You get the location.
Yeah.
I mean, you can easily do this yourself, right? You have to pass the CSV and basically go there and get the intensity out. I mean, I always thought that many of these things you can use and do something else.
Yeah. You have all the positions.
Because we're trying to support other standards so that you can easily go to other softwares like Michael here wants to write and data export instead of just CSVs and stuff like that, that we are more compatible with the tools that are out there. Because there's still some normalization, standardization missing. For all these tools, everybody writes something else. It's really evil, actually. The MATLAB tools, for example, they have offsets of 0.5 pixels in X and 1 pixel in Z relative to the Python and Java-based tools.
Well, it's always fun.
That is really evil. There's a little chapter in our paper about this, how each of them does it. So that's really evil. Because, for example, Tim was doing simulation in MATLAB, and we ran this in Java, and everything was off by, you realize, right? But if you just run the experiment, you might not realize. That's actually interestingly happened to the EasyFish people. They ran Tim's MATLAB software.
Yeah, like with the overlay.
Exactly. I was like, this was all a bit off. Why does this all look a bit off? Exactly. 0.5 pixels in X and 1 pixel in Z. Because then you run it with cellpose, right? Or some detection that's again Python or Java based, right? And they again have different offsets. Because in Java, in MATLAB, image starts at C1, not at C0. They have 1 based. And then you have to decide where's your pixel, right? Top left corner, middle, these types of things. So you have to be careful with these things. If you go from one software to the other to access pixel values of the same image. So then you press OK. Then you have your list of the multi-fish localizations that you can then save as CSV. Then that's it. One thing you can do immediately here is go back and overlay the results. For example, in the data view, it will automatically say display the processed image with the points that are currently in the result table, which is kind of the standard that you want to do. And you can look at this in 3D, right? That's the same that you saw for the big EasyFish data set. Nice thing here, you can easier look at this in 3D. Points are at the right location, if everything was found, or at least you get a good feeling for it, right? You get to live north and see, convince yourself. It's plotted as a Gaussian in 3D. That means you see it. The ones that are a bit further away are just dimmer. So that's nice as you go through. And this works pretty well. I really like this tool as a confirmation. When I compare different softwares, I just use our plotting tool just to see, to go in there and confirm that things are right. So yeah, if you now were to do this again, and you can do plugins macro record, macro, do the same thing again, RSFish. Now instead of doing interactive, you simply do advanced. And instead of it asks you all these things that we put in by hand, and it autofilled everything that we put in interactive mode. So here is the only way to use multi-threading. It's actually in the advanced mode. The reason for that is that I only put it there. This is much faster, right? You can distribute it, but you get slightly different results, which is due to the fact that RANSAC is the stochastic method. And usually, if you run it on the entire image, you run the same thing again, it will still detect them in the same order, run the RANSAC in the same order, meaning we get the identical result out. If you run little blocks, each of these blocks is its own thread, and the different random numbers are just different. And by that, you might get slightly different results. And yeah. But of course, if you want to automate this, it is actually faster. And you can also here specify results file then. If you run an advanced mode, you can say save it to that CSV, but you don't have to do extra save as. You could report this to, but it's easier to just specify the CSV. That's it. Sigma RANSAC, spot special. I'm not going to run it now again. It's just the same. Then you get your run command. You can create your macro. Images. Any questions until here? Because that kind of summarizes the first part, the Fiji part of it. An incredible explainer, or it's incredibly boring?
Or incredibly easy.
So we wanted to make this available as a command line because many people are used to this. They have their notebooks, they have their things, and actually, there's one of the things you always want to do is also provide this as a conda package where you can just conda install RSFish and all the commands come. Right now what you do is do git clone the RSFish, for example. You clone it in this directory, git clone, get this from here, right? You can only do HTTPS, you do this, clones it into this directory. I can actually do it again. It's a bit slow because we have some example images there, which is not good style, but at the same time. We didn't have Figshare back then. It is an install script. It installs it locally. You have to have Maven and Java installed for this to work. This is also explained in on the GitHub side. This is very easy for Mac and Linux, a bit harder on Windows as usual. But on Windows, you can use Fiji. I don't know many Windows people like to use the command line because that's a weird combo thing. That you would use Windows in the first place. There are exceptions, I know, but sometimes you're a lot of drivers, or so you have to use it, right? But so then it tells you, look, I installed all these commands, RSFish, isotropy, the overlay, and the embryo correction that is actually to remove this for a project that we had. It's actually interesting. So what this does is it realizes that the points get dimmer in Z as you go through the data set, right? Because simply it sounds pretty thick. Fits a quadratic, that's where the quadratic function comes from, fits a quadratic function to it to correct this decrease in intensity as you go through the sample. So we used it because we actually needed the intensities because we were extracting transcription sites, and tells you what is transcription sites. We need to actually amplify the transcription intensity. That's good. So, but I don't need this here. And now basically you can do the same thing in the command line that we just did with Fiji. It actually can launch Fiji if you want to do so. That's the first example that I have here. You can run it with interactive. Basically, what it really wants from you is the input image and the output file, right? Which image you want to process and where you want to send it to. We do ---- interactive. like here. It will open it and provide you the same thing. Right? No, that's nice. You don't need to worry about update sites, and you can just do that instead. I will not do it like this. I will just try it without interactive now, because then it will simply run it through. With default parameters, right? So that's all of this now. It's radial symmetry. It's not multi-threaded, right? This is really the basic plane. You just type in what's this outfit without the required parameters. It will tell you what you can do, what the parameters are. Because you can set all the parameters that you also set in the UI. For example, you could even record your macro. You get all the names are the same, and just put this in the command line and run this. So where did I save it to? So yeah, here, right? So now it created this CSV file here automatically. You can easily look at it, same as with the Fiji version. So there's the CSV overlay, BDB. Doesn't have so many parameters, but here is the point offset that was added for CSVs created by MATLAB. So that it will give you the same that we already had. Questions? Makes sense. 2D works as well. I mean, always so 3D data, 2D works as well. Like it's not limited. We also have the not the overlay BDV, but the overlay image, which is also sometimes useful. It then opens the image and basically overlays this here as these little increasing circles, just to confirm that this is right. This, of course, only works on smaller images, etc. It also, I didn't go into this now, but you have also the anisotropy tool. Hope this works. Yeah, just give it an image. Yeah, that's interactive, so it will pop up. You have to define, and then it will give you this back. So yeah, that's basically the same thing from the command line, right? So now I want it to be more interesting and look at larger volumes. So I just want to show you just how this looks like. This is just one of the data sets that I stole now from Johan. It's still on the NRS.
Question first. So how much does install
Can
actually?
you talk a bit louder? I don't think
How much does install actually do at this point? So
it builds. It does the Maven build and creates scripts. It creates scripts. So, for example,
so it needs the Java virtual machine installed.
Yeah.
It needs Maven.
basically it creates this, sets the memory. There's some magic how to determine the system memory, blah 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 blah, and the rest is basically output from Maven. And it adds like what are the dependencies. And that works very robustly on Mac, on Linux. I haven't really tried it on Windows. I think it should work as well in the subsystem. But the hard part is to have made the Java installed, otherwise it doesn't work. I think that is the reason why people still started building Docker containers around this, because then you have to get rid of this aspect of it. Okay, bigger volume. There's this cool tool N5 utils from Saalfeld, which is there to just view large N5s or ZARs. You can just look at this. Oh, no, so that's one of these easy fish volumes. It's a bit slow here on the fine. But you get the idea, right? It's like pretty big volume full of RNAs, or not so full. Depends on the gene, right? But it's like 10,000 by 10,000 by a few thousand pixels, so pretty substantial volumes. So assume you want to run this now in such a big volume, right? So what you would do is basically open that volume, import M5, which also opens SAR and HDF5. By the way, it doesn't have to be M5. It should be renamed. I just copy and paste the path in here, which I did here. Detect data sets. In channel 1, you have these volumes. So obviously we can't open the full REST thing, 160 gigabytes. But what we can do is, for example, go back here into this and find a little area that we're interested in. Say, because at the end we want to tune the parameters so it works on the big data set. So for that we can basically say, look, let's go with this part here. Reasonable. So what you can do then is say we open this one, but we open a crop. We don't open the whole thing, just a crop of it. Then it asks you min and max of the dim. That means we go here, say from, you see, 1300 basically in X, right? You see it up there. Till, let's say, 1500. While it's not here, 1150. 1 to 80, and then see maybe from here 6, 8, 30, 720, something like this. Like a reasonable sized. Open that. Got it already. Right, we open just this one little piece. Now we can do the RSFish workflow, right? Basically segment this part. We can do the isotropy. Yeah, annoying thing, they come up with no name. So you have to give it a name. Something to fix. You will find enough to isotropy. .7, similar. So that's something that typically remind for the next meeting. Oh, it's a view, Mark. So yay.
Right here.
So now what you would do is basically go to Spark and run it on this big volume. As I don't want to do this now because it is pretty quick, but it still runs an hour on such 150 gigabyte volume. So what I would do instead is basically take our Drosophila sample, resave this as an N5 and run it there with Spark. But it would be, you could run it the same on a big one. And with Spark, you can run it locally, but also on the cluster. So we have all the scripts to set up to run this basically on a Janelia compute cluster on large volumes. Or many images, just as Spark. Okay. So for that, I reopen this beautiful C elegance. We save this as an N5. Numbered everything. Folder. I call this. It's called the same way. Changed it. And done. Make the data set here. We can use N5 view to open this. And voila. Once we figure out there's something weird to the density, there's our C elegance, right? Now we save this N5. So nothing crazy, just different format. Now comes the interesting part, right? Now we want to run a distribution. Assume that's a terabyte volume. And at this point, it doesn't matter. And for this, we have the RSFish Spark repository. That is basically the same as RSFish, just with the Spark dependencies, and they come with a pain because you have like so many dependencies that it's always hard to get everything in order. That's why usually there's a project and then a Spark project that basically imports all functionality and runs it simply distributed. So I prepared that command. But basically it's the same thing. You clone now RSFish Spark instead of RSFish, you call it style, same. Then you have this RSFish Spark. And same, it tells you what it needs. I need the image, the data set, the output, min intensity, max intensity. It needs to know this now, right? Because each Spark worker will only look at its block. We could make it look at the entire image, but that would make it so slow if every block would try to figure out the min and max of the entire image before running. That just makes no sense, right? So that's why it wants to know the min and max. It's not that you have to know it. You can just, when you do it in Fiji, I do 0 to 65535, and that's it. You can do it. It doesn't have to be actual values. It just has to be consistent, right? That the parameters you find work with this min and max. It doesn't, of course, it doesn't harm to do it right, but at the same time, it doesn't have to be right. It can just be. It has to be, you have to use the same ones in the active mode as when you run it. And there are thousands other things, again, all the parameters that RSFish has, you could do. So just quickly, RSFish Spark, dataset is the one that we saved. The export, the dataset M5, in there, it's channel 0, C0, S0. So that would be a multi-resolution pyramid if there would be, but there's not, it's just full resolution data as it is. Min intensity and max intensity, I set to the actual values. Anisotropy, I set to 1.0 is not correct, but as I said, it doesn't get that much. And the output, I just named it .spark.csv. It runs. Spark has an overhead for starting and closing, so it's not very efficient for these small ones. Simply multi-threaded would be faster than running Spark, but it's more about that to test out, and it's done. And it's saved here the Spark CSV. It's a tiny bit different as expected, right? The parameters are not identical, and it's run in blocks, so there are small differences, but differences are marginal.
It was parallelized, or it's not?
It was what
It's based on the block size that you're using.
Yes.
Where was that specified?
It does something by default, but I think you can also define it.
Oh, okay, default.
Yeah, you can set the block size as you want. But by default, it will use as you saved it. But then you can say, I want bigger or smaller, or these are like performance considerations sometimes.
Just for curiosity, what happens if you have a spot like right along the demarcation between blocks?
That works. This will be
There's
exactly the same as if the block would be 5 over. It's completely agnostic.
I mean, would it find 2 spots?
There's one exactly as if there was no block border. That works. That's simply, but somewhere, so because every block takes a little bit extra.
Okay.
And you take as much extra as you need to compute the difference of Gaussian, which depends on the radius. But we basically say open the entire image, but due to N5, you say open the entire image, it doesn't actually open the image. It only loads the data when you actually access it. So when you make this block, it will load all surrounding blocks to be able to do the border. So as if you do one block, it actually opens 9 blocks. That's what it needs to do, right? Because otherwise the data is not there. But that's why then it knows exactly is the point here or here, and the respective block will keep it only if it's here or here. So it's really identical to running it without blocks. The only difference is, as I said, since the RANSAC is based on a stochastic process, that's a tiny bit different. And there's not much you can do about that. So yeah, and then we can look at that. Oh yeah, you have to go back to the RSFish directory because the Spark only has the execution. And we look at basically the same. But now it was computed with Spark in parallel. So for example, this 150 gigabyte volume from EasyFish, I ran this on my notebook, on my workstation. That took like 50 minutes. You do the same thing with FishQuant. that did it initially, it was like 8 hours for the same thing. So there is some advantage. Plus, you can afterwards go and just look, how does it look? Are they actually the right spot? And so on and so on and so on. So yeah. With that, I conclude my how-to session. If there's anything, if you want to use it or something, just always can ask us, for help or something. But it should be rather self-explanatory as long as the images are not too big. Spark is always a bit of a, need some experience there. Because with every distribution technique, like also running it on the cloud.
Yes, you're still having problems with the floss.
Yeah, don't have it installed. But it's okay. Pretty annoying that it always pops up even if I don't load the floss data. I keep talking to Stephan about it at some point.